Tonight, we follow the story of binary stars, pairs of suns bound together by gravity, moving through space in quiet balance. Welcome to the Orbit for Sleep channel. Here, science unfolds slowly, gently, and without urgency. Let us follow the orbit of science and drift gently towards sleep. You drift away from a familiar kind of sky. The idea of a single sun, steady and alone, begins to loosen its grip in its place. Another scene slowly forms. Two bright bodies move together through space, not colliding, not separating, but bound in a quiet, repeating motion. Their light overlaps. Their gravity shapes a shared path. This is not an unusual exception in the universe. It is one of its most common arrangements. In astronomy, this system is known as a binary star system. Two stars are held together by gravity, orbiting a shared center of mass. That center is often invisible, suspended in empty space between them. Neither star truly sits still. Each responds to the pull of the other, creating a balance that can last for millions or even billions of years. This paired motion can be imagined through something simple. Two people holding hands on a frozen lake begin to spin. Neither person stands at the center. Instead, both circle point between them, adjusting their speed to keep the motion smooth. In space, gravity plays the role of those joined hands, maintaining the motion without friction or sound. Binary stars are not rare. Observations across the Milky Way show that many stars form in pairs or small groups. During the collapse of large clouds of gas and dust, rotation and turbulence often cause the material to split. Instead of one star igniting, two cores grow side by side, each feeding on the same cloud. When nuclear fusion begins, two stars are born together, already linked. Their appearances can differ. Some binary stars are nearly identical in size and brightness, moving like twins in a carefully practiced dance. Others are mismatched. One may shine intensely, while the other glows more softly. In some systems, a dense stellar remnant, such as a white dwarf or neutron star, circles a normal star, altering its behavior through gravity alone. From a distance, these systems appear calm, yet their influence is profound. Binary stars help astronomers measure stellar mass, test theories of gravity, and understand how stars evolve. Their steady motion reveals laws that apply across the universe. As the scene settles, the idea of isolation fades. In this universe, light often forms in partnership. Motion emerges from relationship. Even stars, vast and powerful, are shaped by the presence of another. In quiet contrast to the image of a lone star shining at the center of a system, a binary star system is defined by shared motion. Two stars move through space together, linked by gravity, orbiting a common center of mass. This center is not always located within either star. Often, it exists as an empty point in space, defined only by balance. The physics behind this motion remains simple and steady. Gravity pulls each star toward the other, while their forward motion prevents collapse. The result is a stable orbit, similar to the way Earth remains bound to the Sun. In a binary system, however, neither star acts as a fixed anchor. Both are constantly in motion, adjusting to their partner. Binary systems vary widely in scale. Some pairs orbit at distances similar to the space between Earth and the Sun. Others are so close that their outer layers nearly touch. In these compact systems, gravity can stretch stellar surfaces into elongated shapes, subtly changing how the stars release light and heat. Astronomers identify binary stars through several observational methods. Visual binaries appear as two distinct points of light through telescopes. Spectroscopic binaries are revealed through small shifts in the color of their light, caused by motion toward and away from Earth. Eclipsing binaries show rhythmic changes in brightness as one star passes in front of the other. A simple comparison brings clarity. Two dancers moving together adjust their pace continuously, maintaining balance without spoken instruction. Neither dancer remains still. In space, gravity performs this role with precision, guiding motion without friction or sound. Understanding what binary stars truly are allows scientists to measure stellar mass with accuracy. These measurements support nearly all modern theories of stellar structure and evolution. Binary stars, through their shared motion, quietly define how stars are understood across the universe. When stars are imagined as solitary points of light, it reflects familiarity rather than reality. In the regions where stars are born, isolation is rare. Stars form inside vast clouds of gas and dust, known as molecular clouds, where gravity pulls material inward from many directions at once. As a cloud collapses, it rarely does so smoothly. Rotation, turbulence, and uneven density cause the cloud to fragment. Instead of forming a single central core, the material often separates into multiple dense regions. Each of these regions continues to collapse, heating up until nuclear fusion begins. In this way, two stars can ignite side by side, already bound by gravity from their shared origin. A simple everyday comparison helps explain this process. When water drains from a large basin, it does not form one perfect funnel. Several swirling motions appear at once, each shaped by small differences in flow. Star-forming clouds behave in a similar way, responding to tiny irregularities that grow over time. Observations of young star clusters support this picture. In these crowded environments, stars are found close together, moving through space in groups. Gravitational interactions during their early lives can lock pairs into stable orbits, while others are gently pushed away. Many stars that appear alone today may once have formed as part of a pair. Studies across the Milky Way reveal that binary and multiple star systems are especially common among massive stars. Their large amounts of material and stronger gravity increase the likelihood of fragmentation during formation. Smaller stars also frequently form in pairs, though their companions can be harder to detect. This pattern reshapes how stellar evolution is understood. If most stars begin life with a companion, then interaction is not a special case but a standard condition. Mass transfer, orbital shifts, and shared influence become natural outcomes rather than rare events. Seen from this perspective, solitude is not the default state of stars. The universe tends towards systems, connections, and shared histories. Many points of light in the night sky carry the quiet imprint of a partnership formed at birth. Gravity is the quiet force that allows two stars to remain close without merging. In a binary star system, each star pulls on the other continuously. This mutual attraction bends their paths into repeating orbits, shaping a stable pattern that can persist across vast stretches of time. The motion follows a shared rule. Both stars orbit a common center of mass, a balance point determined by their relative masses. If the stars are similar in size, that center lies between them. If one star is much heavier, the center shifts closer to the larger body. As they glide outward, the rope tightens, pulling them inward. As they move inward, their speed increases, preventing collision. In space, gravity replaces the rope, and motion replaces friction. The balance emerges naturally, without adjustment. The understanding of this force developed over time. In the 17th century,
Isaac Newton described gravity as a universal attraction between masses. His work provided the framework to explain why planets orbit stars and why stars in a binary system remain bound. Later observations confirm that the same laws apply far beyond the solar system. Gravity does more than hold stars together. It shapes their structure. In close binary systems,
the gravitational pull can distort stellar surfaces, drawing material from one star to the other. This transfer of mass changes temperature, brightness, and lifespan, altering the future of both stars. From a distance, gravity appears invisible. Its presence is revealed only through motion. The steady rhythm of binary stars traces gravity's influence across space, offering a clear demonstration of a force that governs galaxies, stars, and planets alike. In binary systems, gravity does not act as a constraint. It acts as a connection. Two immense sources of energy remain distinct, yet linked, each shaping the path of the other through constant, silent influence. For much of human history, stars appeared fixed and solitary. Their distances were too great, their motions too subtle. Early astronomers recorded positions and brightness, assuming each point of light belonged to a single object. The idea that some stars moved in pairs took time to emerge. The first clear clues appeared through careful observation rather than sudden discovery. In the 17th century, astronomers using early telescopes noticed that certain stars seemed unusually close together. At first, these pairs were thought to be chance alignments, two unrelated stars lying along the same line of sight. Over decades, patient measurement changed that view. Some of these paired stars slowly shifted position relative to each other, while maintaining a consistent relationship. Their motion suggested connection rather than coincidence. By the 18th century, astronomers began to recognize that gravity could bind stars just as it binds planets. A useful comparison comes from everyday experience. Two distant cars, seen from far away, may appear side by chance. Over time, if they continue to move together along the same road, their shared motion reveals a relationship. In the sky, repeated observation served the same purpose. The work of William Herschel in the late 18th century proved especially important. By tracking stellar pairs across many years, he demonstrated that some stars orbit one another. This was the first evidence that Newton's laws of gravity extended beyond the solar system, governing stars themselves. Later discoveries refined this understanding. In the 19th century, spectroscopic techniques revealed binary stars too close to be visually separated. Small shifts in starlight showed motion toward and away from Earth, confirming orbital movement through light alone. Through these methods, binary stars became tools rather than curiosities. Their motion allowed astronomers to measure stellar mass directly, grounding stellar science in observation. What began as faint doubling in a telescope became a foundation for understanding how stars exist, interact, and endure across the universe. In many binary star systems, the two stars never collide. Their paths curve endlessly around each other, maintaining separation through motion rather than distance alone. These stable paths are known as orbits, shaped by gravity and momentum working together. Each star follows an elliptical path, not a perfect circle. The shape of that ellipse depends on the system's total mass and the speed at which the stars move. As one star draws closer, its speed increases. As it moves farther away, it slows. This constant exchange between distance and speed prevents contact, even across millions of repeated cycles. A familiar example helps clarify this balance. When a stone is tied to a string and swung through the air, the stone does not fall inward as long as it keeps moving. The tension of the string pulls it inward, while motion carries it forward. In a binary system, gravity replaces the string, and inertia replaces the hand. These orbits can exist at many scales. Some stars circle each other at distances greater than the span of our solar system. Others orbit so closely that their surfaces are separated by only a few stellar diameters. Even in these tight arrangements, collision is avoided unless energy is lost through external forces. The long-term stability of such orbits reveals important natural processes. Over time, interactions with nearby stars or passing gas clouds can alter orbital paths. Small changes accumulate slowly, sometimes tightening or widening the orbit. Despite this, many binary systems remain intact for billions of years. Astronomers use orbital motion to extract hidden information. By measuring orbital period and separation, they calculate stellar mass and density. These values anchor modern stellar physics, offering insight into how stars generate energy and age over time. Orbits that never touch illustrate a broader pattern in the universe. Stability often arises not from stillness, but from motion carefully balanced. In binary stars, separation is preserved through constant movement, tracing invisible paths that repeat with quiet precision across cosmic time. In some binary star systems, separation is maintained, yet interaction becomes unavoidable. When two stars orbit closely enough, gravity can extend its influence beyond motion alone. Material from one star may begin to drift toward the other, creating a shared system of light and mass. This process begins when a star expands during its natural evolution. As it ages, its outer layers can swell outward. If these layers cross a gravitational boundary known as the Roche limit, matter no longer remains bound to its original star. Instead, gas flows slowly toward the companion, guided by gravity. A simple comparison can be found in everyday life. When water fills a tilted container, it naturally spills toward the lower side once the edge is reached. In a close binary system, gravity defines that edge. Once crossed, transfer becomes steady and predictable. The exchange of mass changes both stars. The receiving star may grow hotter and brighter as fresh material fuels its core. The donating star, having lost mass, can cool or collapse into a denser state. In some systems, this interaction creates an accretion disk, a glowing ring of gas spiraling inward, releasing energy as it moves. Astronomers first recognized these processes through changes in brightness and spectral signatures. In the 20th century, observations revealed stars behaving in ways that could not be explained by isolation. Only interaction could account for their shifting light and unexpected temperatures. These shared systems play a critical role in cosmic events. Many stellar explosions, including certain types of supernovae, arise from mass transfer within binary stars. What appears calm from afar can contain powerful transformations driven by gradual exchange. Binary stars that share their light and mass demonstrate how connection reshapes evolution. Through steady transfer rather than sudden force, one star alters the future of another, revealing a universe where change often occurs through quiet, continuous interaction. Some binary star systems reveal their presence not through separation, but through rhythm. As the two stars orbit, one periodically passes in front of the other from Earth's point of view. When this happens, the system's total brightness gently decreases, then returns to normal. These systems are known as eclipsing binaries. The process is regular and precise. Each orbit produces a repeating pattern of dimming and brightening tied directly to the star's motion. The timing of these changes reflects the orbital period, while the depth of the dimming reveals the relative sizes and brightness of the stars involved. An everyday comparison helps clarify this effect. When a person walks past a window at night, the light inside briefly fades before returning. The light source has not changed. Only the path between observer and light has shifted. In eclipsing binaries, motion alone shapes what is seen. Astronomers began recognizing this pattern in the 19th century, long before the stars themselves could be resolved. Careful measurement of brightness over time revealed repeating cycles that could only be explained by mutual eclipses. This made eclipsing binaries some of the earliest systems used to study stellar structure. These systems offer unusually clear information. By analyzing how light changes during an eclipse, scientists determine stellar size, mass, and density with high precision. The method relies on geometry rather than assumption, making eclipsing binaries reliable benchmarks in stellar science. Beyond measurement, eclipses reveal interaction. In close systems, tidal forces distort stellar shapes, altering the eclipse profile. Gas flowing between stars can further modify light patterns, adding subtle variation to an otherwise steady rhythm. Eclipsing binary systems show how motion translates into visibility. Through repeated passage and alignment, hidden structure becomes observable. What cannot be seen directly is revealed through time, pattern, and the steady logic of orbiting light. When two stars orbit closely, gravity does more than guide their path through space. It extends inward, reaching into their very structure and slowly reshaping them over time. This subtle but persistent influence is known as tidal force, the same factor effect responsible for the rise and fall of oceans on Earth under the pull of the Moon. In a binary star system, tidal forces arise because gravity is not applied evenly across a star. The side facing its companion experiences a slightly stronger pull than the side facing away. This difference creates stress within the star, drawing material outward along the line that connects the two bodies. As a result, the star no longer remains perfectly spherical. Its shape becomes gently elongated, responding continuously to its partner's presence. A familiar comparison can be found along Earth's coastlines. Ocean water responds to the Moon's gravity, forming tides that rise and fall each day. Less visibly, the solid Earth also flexes by small amounts. In space, stars behave in a similar way. Though composed of hot plasma rather than rock or water, they remain responsive to gravitational imbalance, adjusting their shape slowly rather than abruptly. These tidal interactions influence how stars rotate. Over long periods, energy is redistributed within the system. Friction inside the stars gradually slows mismatched motion, allowing rotation to synchronize with orbit. This process, known as tidal locking, results in one side of a star consistently facing its companion. While this outcome takes millions of years, it represents a stable and energy-efficient configuration. Astronomers identified tidal effects in binary stars through careful observation. Variations in brightness, shifts in orbital timing, and changes in rotational speed provided evidence that gravity was reshaping stars from within. By the 20th century, improved measurement techniques revealed stars rotating more slowly than expected, their behavior shaped by prolonged interaction rather than solitary evolution. Tidal forces also influence internal energy flow. As stars are stretched and relaxed during each orbit, mechanical energy is converted into heat. This heating affects temperature distribution within the outer layers and can subtly modify how gas moves across stellar surfaces. In close binary systems, tidal heating works alongside mass transfer, amplifying long-term change. Through tidal forces, binary stars exchange more than mass and light. They exchange shape, rotation, and internal energy. These effects accumulate gradually, almost imperceptibly, yet they leave lasting marks on stellar evolution. Over time, gravity's uneven pool sculpts both stars, preserving their partnership while quietly transforming what they are. In certain binary star systems, interaction goes beyond influence and becomes transformation. Over long periods, the evolution of one star can directly alter the fate of its companion. What begins as a balanced orbit can gradually shift into a system where change flows in only one direction. As stars age, their internal processes change. A star that exhausts hydrogen in its core begins to expand, entering a later stage of stellar life. In a close binary system, this expansion can bring the star into strong gravitational contact with its partner. Once this threshold is crossed, material no longer remains confined to its original star. Gas begins to move from one star to the other, guided by gravity. This transfer does not occur suddenly. It unfolds gradually, forming streams and disks of matter that spiral toward the receiving star. A familiar comparison appears when sand slowly pours from one container into another. The shape of both containers matters, but gravity determines the direction of flow. The receiving star changes as it gains mass. Its temperature can rise, its brightness can increase, and its internal pressure can shift its future evolution. At the same time, the donating star weakens. Having lost outer layers, it may shrink into a compact remnant, such as a white dwarf, retaining only its dense core. Astronomers came to understand these processes through observation of unexpected behavior. In the 20th century, certain stars were found to burn hotter or longer than theory predicted. Others faded too quickly. These discrepancies made sense only when stellar interaction was included. In extreme cases, the consequences become dramatic. If a white dwarf gains enough mass from a companion, internal pressure can reach a critical limit. The result may be a powerful stellar explosion, releasing energy across space and briefly outshining entire galaxies. Binary systems reveal that stellar evolution is not always a solitary path. One star's aging can redirect the life of another. Through steady exchange rather than sudden collision, gravity and time combine to determine which stars fade quietly and which end in transformation. In regions where two stars share a system, planets must form under conditions very different from those around a single star. The presence of a second source of gravity reshapes the environment from the beginning, influencing how dust, gas, and motion organize themselves. Planet formation begins inside a rotating disk of gas and dust. Around a single star, this disk settles into a relatively simple, flat structure. In a binary star system, gravity from the companion star disturbs this disk. Material can be stretched, tilted, or broken into rings depending on the star's distance and mass. A useful everyday comparison can be found in water stirred by two rotating spoons. Instead of forming one smooth whirlpool, the surface becomes complex, with shifting currents and unstable regions. In space, gravity replaces the spoons, shaping patterns that are dynamic rather than uniform. Despite this complexity, planets do form in binary systems. Observations have revealed two main arrangements. Some planets orbit closely around one star, while the second star remains distant. Others follow wide paths around both stars, circling the pair as a single gravitational unit. Each configuration reflects a balance between motion and stability. Astronomers confirmed the existence of such planets in the late 20th century when precise measurements detected subtle changes in starlight caused by orbiting worlds. These discoveries demonstrated that planet formation is resilient, capable of adapting to environments once thought too chaotic. The properties of these planets can differ from those in single-star systems. Their climates may change more dramatically as stellar light varies. Orbital paths can shift slowly over time, responding to the combined pull of two stars. Yet many remain stable for billions of years. Binary star systems show that planet formation does not require simplicity. Even under competing gravitational forces, matter can settle, organize, and endure. Worlds can rise not despite complexity, but within it, shaped by the steady influence of two suns rather than one. Life, as it is understood on Earth, depends on stability. Temperature, light, and time follow predictable patterns. In a binary star system, these conditions are shaped by more than one source, creating environments that change in ways unfamiliar to a single sun world. On planets orbiting one star within a binary system, the second star can still exert influence. Its light may appear periodically in the sky, brightening seasons or subtly warming the planet at regular intervals. These variations depend on distance and orbital alignment, sometimes unfolding over years rather than days. A simple comparison can be drawn from everyday experience. Living near the ocean, temperatures tend to fluctuate less sharply due to the moderating effect of water. In a binary system, the second star can act as a distant modifier, altering climate patterns without dominating them. In systems where planets orbit both stars together, conditions become more complex. Light arrives from changing angles, and the length of day can vary. Despite this, models show that stable orbits exist where energy input remains balanced over long periods. Stability, rather than simplicity, becomes the key requirement. Scientific interest in these environments grew in the late 20th century as discoveries of planets in binary systems accumulated. Computer simulations demonstrated that liquid water, a basic requirement for known life, could persist under certain orbital conditions. Habitability expanded from a narrow definition to a broader spectrum. Life does not require uniformity. On Earth, organisms adapt to seasonal shifts, eclipses, and irregular climates. In binary systems, adaptation would involve responding to dual cycles of light and shadow, learning to thrive amid layered rhythms. Binary stars suggest that life, if it arises elsewhere, may do so under conditions shaped by relationship rather than isolation. Two suns do not exclude the possibility of living worlds. They redefine the patterns under which life might quietly emerge and endure. On Earth, the cycle of day and night is simple and reliable. One planet turns beneath one star, creating a steady alternation of light and darkness. In a binary star system, this rhythm becomes layered, shaped by multiple motions unfolded at different speeds. For planets that orbit a single star within a binary system, the primary source of daylight remains familiar. The planet rotates, and its star rises and sets in a regular pattern. Yet a second sun may appear in the sky as well, sometimes faint, sometimes bright, depending on distance and alignment. Its presence can extend twilight or soften the boundary between day and night. An everyday comparison helps make sense of this experience. In cities with strong artificial lighting, night never becomes fully dark. Streetlights and distant buildings blur the transition. In a binary system, the second star can play a similar role, adding light without fully replacing the main cycle. In systems where planets orbit both stars together, the pattern changes more dramatically. Day length can vary as the two stars move relative to the planet. Light may arrive from shifting angles, and shadows can stretch or overlap. Despite this complexity, the motion remains governed by predictable orbits rather than randomness. Astronomers began modeling these environments in the late 20th century, using computer simulations to track how light exposure changes over time. These models showed that even with two suns, repeating patterns emerge. The cycles may be longer or less uniform, but they remain stable. Such conditions would shape any environment that develops there. Temperature regulation, weather patterns, and biological rhythms would adapt to layered light cycles. On Earth, life responds to daily and seasonal cues. In a binary system, those cues would be richer, combining multiple overlapping clocks. Day and night under two suns are not defined by chaos. They are defined by interaction. Multiple motions combine to create a rhythm that is more complex, yet still ordered, revealing how time itself can feel different when shaped by more than one star. Long before binary stars were understood as physical systems, humans noticed the presence of paired lights in the sky. Without telescopes or equations, early observers relied on pattern and repetition. When two stars appeared close together and moved in subtle relation over time, they invited interpretation rather than explanation. Across cultures, paired stars often became symbols. In some traditions, they were seen as siblings, lovers, or rivals, their proximity suggesting connection rather than chance. These stories did not arise from precise measurement, but from long familiarity. The night sky was observed carefully, season after season, century after century. A simple comparison exists in everyday life. When two distant mountains appear side by side on the horizon, they are often named together and remembered as a pair. Meaning forms naturally around proximity. In the same way, stars that shared the sky became linked in human thought. Ancient mythologies frequently used twin figures to represent balance or duality. Light and dark, order and chaos, protection and danger were often expressed through pairs. Binary stars fit naturally into this framework, even when their physical relationship remained unknown. As astronomy developed, some of these paired stars gained scientific attention. In the 17th and 18th centuries, telescopic observation began to separate myth from measurement. Yet the language of partnership remained. Stars once described through story became objects of study without losing their symbolic weight. This overlap between imagination and observation shaped early science. Familiar stories made the sky memorable, while careful tracking transformed meaning into knowledge. Binary stars sit at this intersection where human narrative and natural motion aligned. Even today, the idea of two suns carries emotional resonance. It suggests relationship rather than solitude, connection rather than isolation. Long before equations described gravity and orbit, human imagination recognized that some lights in the sky seemed meant to exist together. As scientific understanding expanded, binary stars moved from myth into imagination shaped by modern knowledge. Science fiction became a space where observation and speculation could meet. Worlds beneath two suns appeared not as symbols, but as environments shaped by physical rules. Writers and filmmakers often return to the image of twin suns to signal difference. A sky with two light sources immediately suggests another kind of world, one governed by unfamiliar rhythms. Yet many of these imagined systems remain grounded in real astrophysics, drawing directly from what is known about binary stars. A simple parallel can be found in everyday design. Cities built around rivers feel different from those built along coastlines, even when both support human life. The environment shapes behavior. In the same way, planets under two suns invite stories that explore how altered light and time affect societies. In science fiction, binary star worlds often feature extended days, dramatic sunsets, or complex seasons. These details reflect real consequences of dual illumination. The movement of two stars across the sky would shape agriculture, architecture, and daily routines, not through fantasy alone, but through predictable physical influence. During the 20th century, as astronomy confirmed the prevalence of binary systems, these fictional settings gained credibility. Writers began consulting scientific models, aligning imagined worlds with stable orbits and realistic energy balance. Fiction evolved alongside discovery. These stories also explore perspective. A civilization raised beneath two suns would not consider its sky unusual. What appears exotic to an observer becomes ordinary to those who live within it. Science fiction uses this shift to examine how environment defines normality. Through science fiction, binary stars serve as bridges between knowledge and imagination. They allow complex astrophysical systems to be experienced indirectly through story rather than equation. In doing so, they extend scientific understanding into the realm of human meaning, where unfamiliar skies become places that feel lived in rather than distant. Binary star systems offer astronomers something rare in the universe, a natural experiment. Two stars form together, interact, and evolve under the same conditions, allowing comparison that would be impossible with isolated stars. For this reason, binary stars function as cosmic laboratories. In a laboratory on Earth, variables are controlled to reveal cause and effect. In space, control is replaced by observation over time. Binary systems provide paired objects whose motion and interaction can be measured with precision. Their orbits reveal mass, their light reveals temperature, and their timing reveals internal change. A familiar comparison can be made to studying twins in medicine. When two people share a similar origin but experience small differences, those differences become meaningful. In the same way, binary stars allow scientists to isolate the effects of mass, distance, and interaction. Through binary systems, astronomers test fundamental laws. Gravity behaves predictably in these environments, confirming theories first proposed in the 17th century. Stellar evolution models are refined by observing how mass transfer alters lifespan and structure. Without binary stars, many of these theories would remain untested. In the 20th century, advances in spectroscopy and timing made these systems especially valuable. Subtle shifts in light revealed orbital motion and internal processes invisible by sight alone. Binary stars became reference points, anchoring stellar physics to direct measurement rather than assumption. These systems also expose extreme conditions, dense remnants, intense radiation, and rapid orbital periods push physical laws to their limits. By observing how matter behaves under such stress, scientists gain insight into processes that shape galaxies and cosmic structure. Binary stars show that the universe conducts its own experiments continuously, without intention or design. Nature creates conditions that reveal its rules. By observing paired stars in motion, astronomers learn not only how stars behave, but how the universe allows knowledge to emerge through structure, repetition, and time. Binary star systems do not remain fixed. Although their motion appears steady on human timescales, their futures unfold slowly through predictable stages. Gravity, math, and time guide each system toward outcomes shaped by both partnership and change. As binary stars age, their evolution depends strongly on distance and mass. In wide systems, the stars may live most of their lives with little interaction, each following a path similar to a solitary star. Their orbits expand gently as mass is lost through stellar winds, loosening the gravitational bond over billions of years. In closer systems, the future becomes more tightly linked. As one star expands, mass transfer begins, altering the balance of the system. Orbital periods can shrink or grow depending on how material moves. These gradual changes redirect both stars toward new evolutionary paths. A familiar comparison can be found in long-term partnerships on Earth. Two people may influence each other subtly over time, adjusting habits and direction without sudden events. In binary stars, gravity plays this role, guiding slow transformation rather than abrupt disruption. Some futures are quiet. A pair of stars may end as two compact remnants, such as white dwarfs, continuing to orbit long after nuclear fusion has ended. Their motion persists even as their light fades. Other futures are more dramatic. In certain systems, accumulated math can trigger explosive events, reshaping the surrounding space. These moments are brief compared to the system's lifetime, yet they mark decisive transitions. Across all outcomes, one pattern remains constant. Binary star systems evolve together. Their futures are not independent timelines, but shared trajectories shaped by long interaction. Through steady change rather than sudden collapse, binary stars reveal how time and relationship combine to shape the long arc of cosmic evolution. When a universe is imagined, it is often centered on a single star system, like our own. One star, one dominant source of light, and planets arranged in clear order. Binary star systems invite a different comparison, not as anomalies, but as alternative versions of cosmic organization. In a single star system, gravity flows outward from one center. Orbits tend to be simple, and long-term stability is easier to predict. Planet formation follows a relatively uniform disk, and cycles of light and time remain consistent. These conditions favor regularity. Binary star systems introduce an added layer. Gravity now comes from two sources, sometimes equal, sometimes unequal. Orbits adapt by becoming shared, tilted, or nested. Stability still exists, but it emerges through balance rather than simplicity. A familiar comparison can be found in transportation. A town built around one central road develops differently from a city shaped by two major routes. Movement patterns change, intersections form, and alternate paths appear. In space, gravity creates similar structures, guiding motion without intention. From a scientific perspective, comparing these systems reveals how resilient physical laws are. The same equations describe motion in both environments. What changes is not the rules, but the outcomes they produce. This comparison strengthens confidence in universal physics. Observations across the galaxy suggest that binary systems may be as common as single star systems, or more so. This shifts perspective. What feels familiar may not be typical. The universe expresses itself through multiple stable arrangements. By comparing a single star and binary star systems, astronomers gain insight into variation without chaos. Different structures arise from the same principles. Order does not depend on uniformity. It depends on balance, revealing a universe capable of sustaining many forms of stability at once. When a universe is imagined, it is often centered on a single star system like our own. One star, one dominant source of light, and planets arranged in clear order. Binary star systems invite a different comparison, not as anomalies, but as alternative versions of cosmic organization. In a single star system, gravity flows outward from one center. Orbits tend to be simple, and long-term stability is easier to predict. Planet formation follows a relatively uniform disk, and cycles of light and time remain consistent. These conditions favor regularity. Binary star systems introduce an added layer. Gravity now comes from two sources, sometimes equal, sometimes unequal. Orbits adapt by becoming shared, tilted, or nested. Stability still exists, but it emerges through balance rather than simplicity. A familiar comparison can be found in transportation. A town built around one central road develops differently from a city shaped by two major routes. Movement patterns change, intersections form, and alternate paths appear. In space, gravity creates similar structures, guiding motion without intention. From a scientific perspective, comparing these systems reveals how resilient physical laws are. The same equations describe motion in both environments. What changes is not the rules, but the outcomes they produce. This comparison strengthens confidence in universal physics. Observations across the galaxy suggest that binary systems may be as common as single star systems, or more so. This shifts perspective. What feels familiar may not be typical. The universe expresses itself through multiple stable arrangements. By comparing single star and binary star systems, astronomers gain insight into variation without chaos. different structures arise from the same principles. Order does not depend on uniformity. It depends on balance, revealing a universe capable of sustaining many forms of stability at once. Across the universe, change rarely happens in isolation. Binary star systems make this visible at the largest scales. Two stars form together, evolve together, and influence each other across their entire lifetimes. Their histories are not separate lines, but intertwined paths shaped by constant interaction. From birth, gravity links their futures. Material drawn from the same cloud carries shared composition and momentum. As fusion ignites, each star begins its life already responding to the presence of another. Even when distance grows, the connection remains. A familiar comparison appears in natural ecosystems. No organism develops alone. Growth depends on surrounding conditions, competition, and cooperation. In space, stars follow a similar rule. Their evolution reflects environment as much as internal process. Binary systems demonstrate this principle clearly. Mass transfer alters aging. Tidal forces reshape structure. Orbital motion redistributes energy. Each effect arises not from isolation, but from relationship. What one star becomes influences what the other can be. Astronomical observation reinforces this view. Many phenomena once treated as exceptions, unexpected brightness, unusual rotation, sudden transformation, are now understood as outcomes of interaction. By the 20th century, stellar science had shifted from studying individual objects to studying systems. This perspective extends beyond stars. Planets, galaxies, and cosmic structures form through networks of influence. Motion, gravity, and time operate collectively, producing order through connection. Binary stars offer a quiet conclusion to this pattern. They show a universe where evolution unfolds through relationship. Nothing develops entirely alone. Structure emerges not from separation, but from the steady presence of others, shaping change across vast scales of time.